Hi everyone, so this is the third video in the red-black tree video set. Now in this video, I'm just going to go over why the fixes that we do are going to guarantee that I don't break any of my 4 rules. So as you recall, the 4 rules of a red-black tree are these 4 right here. Every node is either red or black, the root is always black, red node cannot have red children, number of black nodes must be the same along any branch from root to null leaf, any root, any subtree's root to any of its null leaves, okay? So why does doing what we do not hurt our tree in any way? Like why can I guarantee that the fixes that we do ensures the coloring rules are maintained, and how we do our insertion ensures the coloring rules are maintained? So first of all, when we do an insertion, we always insert as red. So what that means is that we never add a black node, right? Which means that we will never ever break rule number 4. This is really important. We never break this rule at the moment of insertion, okay? So just by adding a red node, we aren't increasing the number of black nodes anywhere, okay? So we're fine in terms of knowing that what we do never breaks rule number 4. We also never break rule number 1. The node is red, so it's definitely red or black, so we're fine on that. So the only 2 rules that we can ever break is rule number 2 and number 3, okay? Now let's start with rule number 2. Root is always black. Now, if somehow during the insertion process, we turned our node red, why does turning it black not hurt anything? So here I have a tree. Now this is a very general diagram. When it's like this, it means that I have a root and everything else underneath it is part of the tree, right? Now, if the root is red and that's it, we know that we got there without adding black nodes, okay? So if I look inside the subtree, I'm going to have a number of nodes. But what I do know is that if I were to look and I looked at any one branch from here to here, and let's say that I counted the number of black nodes between the root and its any null leaf, okay? And I said, oh, there's like n null leaves initially on one branch, n, okay? Where n could be any number, doesn't matter, okay? It's just bigger than, greater than or equal to 0, okay? So it's just a number, okay? Whatever that number is. Now I know that no matter which branch I look at and I count how many black nodes there are, they will all be n black nodes, okay? Now, if I then suddenly change the root from red to black, what happens? Well, I didn't change anything else in my tree, right? So in here, I still am going to have exactly n black nodes from not counting the root. Okay, before and after is the same. Every single branch has n. So if I turn the root black, what I've done is that at the end, I'm going to have n plus 1 black nodes on any branch. Okay, so on any branch, I'm going to have exactly n plus 1 black nodes. Okay, now I don't know if it's n plus, I don't know what that exact number is. It doesn't really matter. I'm just going to get n plus 1 when I'm done. Okay, so this is what happens when I change the root. Okay, so if that first fix where if the root ever turns red, turn it black, that's not going to harm anything. I'm still going to have the correct number of black nodes. Okay, I didn't break rule number 4. Okay, so the fix is good. Now, what about those other ones that fixed rule number 3? So that was what happens when you break rule 2. What about breaking rule 3? Why does those not hurt? Let's think about what we have here. So here we have the first of the fix, the one where we have a red sibling. Now, I don't know how many black nodes are in any of these subtrees over here, like none of them. I don't really know. I do know, however, that the number of black nodes on every branch is the same because I never broke rule number 4, right? So no matter how I got to this state, I never got into a situation where I would end up with an extra black node like along here or something. It's correct. So what that means is that if I count how many black nodes there are between the root and to a null leaf inside the subtree, And let's say that there are a total of n null leaves in this subtree. What I also know is that the number of black nodes between here and any of these null leaves, and we can pick any null leaf in any of these trees, it really doesn't matter. Okay, so if I count like this number of number of black nodes on from here to here, the number will also be n. It's going to be the same everywhere. Okay, and that also includes the ones that go into the sibling. So if I count like how many black nodes are from here to here, that's also going to be n. Okay, so every branch has n right now. Okay, so what it means is that when I finish this fix, I have to have the same number of black nodes. I can't add an extra black node anywhere. Okay, now, so if I count, so let's label these. Let's label these W, X, and Y, okay? So if I think about how I got to here, I went from this node through here, black, red, and then down to a subtree within W. That number of black nodes is going to be N, okay, beforehand. Okay, so if I go through W, I needed a black node before I hit this red and another black and the root, like if I look at just these two, okay? Now, when I in this case, because the sibling was red, what I did was a color swap. So I exchanged and the grandparent became red and the sibling and parents became black. So if I count how many black nodes there are from here into this, I counted 2 and then the rest of the tree. And over to the to X as well, I counted 2 and then the rest of the tree. Over here, 2 and then the rest of the tree, right? So I need to have 2 before I hit W, X, or Y in this picture, okay? Now, when I finish with this, notice it's 1, 2, 1, 2, okay? Any extra black nodes here, they don't matter because they would have been the same as this side, and we didn't make any changes, okay? So here I have 2 before I hit the W, and there are 2 before I hit the Y, and there are 2 before I hit the Z. Okay, 1, 2, 1, 2, 1, 2. I still have 2, just like I did before. 1, 2, they're just earlier. So this black, instead of being shared between these two subtrees, it's now there's 1 in each, but it's still 1 on every path. Okay. Now, a similar argument can be made for something like a rotation. So it doesn't matter if it's zigzag or zigzag because it's just slightly different configuration, but it's the same principle. If I take a look at the number of black nodes that I have to hit on X, Y, and Z, it's the same before and after. So before the rotation, there were 2 before I got to the subtree X. Sorry, 3, 1, 2, 3. And afterwards, what do I have before X? Afterwards, 1, 2, 3 black nodes. How about Y? 1, 2, red, and then whatever's in Y, right? So 2 before Y. And if I take a look at this, it's 1, 2, and then the Y. And just like over here, 2 before the Z, 1 black, and then whatever these are, and then Z, right? So 1 black, 2 black, and then Z. So you can see that I'm not changing the number of black nodes in the parts that matter, okay? It's exactly the same number, even though it looks different. So this is why I can say that the fixes are not going to fundamentally alter how the red-black tree works. It's going to actually be exactly the same. Or rather, it's not going to change. It's not going to break any of the rules, I should say. So no matter what this change that I do isn't going to break rule number 4 by accident. It's going to keep the number of black nodes the same, even though I've made quite significant modifications to the shape of the tree. Okay, so that's pretty much it, everyone. We'll see you soon. Bye-bye.